Hello everyone, welcome back. For this lesson, we're going to look at another type of method for comparing the difference between two population means. These are called the pool t-tests or a pool t-interval. And these are an alternative to the two-sample t-test or the two-sample t-interval that we covered previously. Okay, so now for these types of inferences, if we have more information about the populations, in particular, if the population variances are equal, then we can instead look at finding a pooled sampled variance for both the confidence intervals and the test statistics. So the way that we will find a pooled sample variance is by using this formula. Okay, so the notation for a pooled variance is going to be SP squared. And you can think of the pooled variance as being a weighted average of the two sample variances. Okay, so here we have S1 squared and S2 squared. Now, the degrees of freedom for the test is the sum of the degrees of freedom for the two individual samples. So the way that we find the degrees of freedom is by adding the two individual degrees of freedom. So we have n1 minus 1 plus n2 minus 1. And this will give us n1 plus n2 minus 2. So how do we check if we have equal variances for the populations? Well, the method that we will use is comparing the two standard deviations. Okay, so if we take the larger standard deviation and divide it by the smaller standard deviation, and if this ratio is smaller than 2, then we can assume equal variances. If the ratio is larger than 2, then we cannot assume that we have equal variances, and we should be using the two-sample t-test or the two-sample t-interval for the comparisons. But if the ratio is smaller than 2, then we should proceed with a pool t-interval or a pool t-test. So now, alternatively, if we have box plots for both groups, then we can look at the interquartile ranges, and if they are similar enough, then we can also use the pool t-test or the pool t-interval. So if we have equal variances, then we can get a better estimate of the standard error. This is called a pooled standard error. So if we replace the two variances by the pooled variance, and if we perform some algebra, then the pooled standard error is given by the pooled standard deviation, which is SP, multiplied by the square root of 1 over the sample sizes. Okay. So the assumptions and conditions are the same as the two-sample t-test, but we have the additional assumption where the variances are equal. Okay, so we have equal variances. Then we're going to use a pool t-test. The null hypothesis for the test is the same, so we have the difference between the two population means, mu1 minus mu2, is equal to the hypothesized difference. And the way that we will find our test statistic is by using a pooled standard error. And again, the pooled standard error is given by this formula, where we calculate a pooled variance by using this equation. So the sampling distribution model that we will use is going to be a t-distribution, and the way that we find the degrees of freedom is by n1 plus n2 minus 2. So we can use our model to obtain the p-value for the test. And again, if we want to find a confidence interval, we'll be looking at using a pooled standard error for calculating the margin of error. Okay, so let's have a look at an example of a pool t-test. So here we have the weights of random samples of chickens of two different breeds, so breeds A and B. and both populations are normally distributed, so even small samples are adequate. At the 5% significance level, determine if there is a difference in the weights of breed A and breed B. Okay, so the first thing is to write down the hypotheses for the test. Okay, so for the null hypothesis, we will look at the difference between the two population means. We'll call them mu sub A minus mu sub B. And we assume that there is no difference. Okay, so mu sub A minus mu sub B is equal to 0. The alternative hypothesis, well, we're looking at testing if there is any difference in the weights between the two different breeds. Okay, so this tells us that the difference between mu of A and mu sub B is not equal to 0. Okay, so there is a difference between the weights. So now let's check the assumptions and conditions for performing the test. So we have independent responses. Okay, so here we're looking at the weights of chickens. So within each breed of chickens, the weight of one chicken should not affect the weights of other chickens. And because we are looking at comparing two different populations, we have the independent groups assumption. So this says that the groups must be independent of each other. So the weight of a breed A chicken should not affect the weights of breed B chickens, and vice versa. So the weights of a breed B chicken should not affect the weights of breed A chickens. Okay, so to check for this assumption, we'll look at randomization. So we're given that we have random samples of chickens, and so this condition is met. And for the other assumption, we need to have normal populations, and we're given that both populations are normally distributed. Okay, so this assumption is also met. So both populations are normally distributed. Okay, so now we need to decide whether to look at using a two-sample t-test or a pool t-test. Okay, so now the only difference between the two tests is whether or not we have equal variances. So now we're going to check for equal variances. Okay, and the way that we will check for equal variances is by comparing the two standard deviations. We're going to take the larger standard deviation and divide it by the smaller standard deviation. Oops. Okay, so we're given that the standard deviations are 0.19, 0.0029 and 0.182574. Okay, so we take the larger standard deviation, so that's 0.190029, and divide this by 0.182574, and this will give us a ratio of 1.0408, and this is smaller than 2. Okay, now because this ratio is smaller than 2, then we can assume equal variances. And we will proceed with a pooled t-test rather than a pooled or a two-sample t-test. All right, so now let's look at finding the test statistic. Okay, now the test statistic is going to be the sample means of each breed of chicken divided by a pooled standard error. Okay, so what we need to calculate is the pooled standard error. And to find the pooled standard error, we need to look at finding a pooled variance. Okay, so let's first find the pooled variance. Okay, so this is SP squared, which is given as NA minus 1 times SA squared plus NB minus 1 times SB squared divided by NA plus NB minus 2. Oops. The sample size for breed A, so we have 9 chickens. So we have 9 minus 1 times the standard deviation of breed A, that's 0.190029 squared, plus the sample size of breed B, so we have 10 chickens, minus 1 times the standard deviation, which is 0.182574 squared, all over 9 plus 10 minus 2. Okay, so this will give us a pooled variance of 0.03464. Okay, so now from the pooled variance, we can calculate the pooled standard deviation. So we take the square root of the pooled variance, So the square root of 0.03464, then we will get the pooled standard deviation, which is 0.186119. Okay, so now we can use this to calculate the pooled standard error. Okay, this is the pooled standard deviation times the square root of 1 over NA plus 1 over NB. Okay, so we have our pooled standard deviation, which was 0.186119. We multiply this by 1 over 9 plus 1 over 10. And the standard error is going to be 0.085515. Okay, so now we can calculate our test statistic. Okay, so we subtract the two means of both chickens. So we have 1.211 minus 1.500 divided by the pooled standard error, so 0.085515, and we get our test statistic, which is negative 3.379. Okay, so we determined our test statistic to be negative 3.379. So now we can find our p-value. Okay, so now we are performing a two-tailed test because our alternative hypothesis is two-tailed. Okay, and so the p-value is going to be the area of both tails. Okay, so what we calculated was our test statistic, which is negative 3.379. And so we want the area of both tails. So the p-value. Okay, now because we want to use the t-table, we can look at finding the area to the right of 3.379 and then multiplying it by 2. So it will be 2 times the area to the right of 3.379. Okay. So now we also need to specify our degrees of freedom. And the degrees of freedom is the sum of the two sample sizes minus 2. So that's 9 plus 10 minus 2, which gives us 17 degrees of freedom. All right. So now let's use our t-table to determine the p-value. So we have 17 degrees of freedom, and we need to locate where 3.379 falls in between, and it falls between these two values. Okay, so now let's write down what these values gives us. So the area to the right of 2.898 has a right tail probability of 0.005 and the area to the right of 3.646 is equal to 0.001. Okay, so now if we wanted to draw these areas, okay, so the area to the right of 2.898 is equal to 0.005, and the area to the right of 3.646 has an area of 0.001. And so what we want to determine is the area to the right of 3.379. Okay, so now the area is going to fall in between both of these two areas. So this tells us that the area to the right of 3.379 is in between 0.001 and 0.005. So now let's use this to determine an interval for the p-value. So the p-value is going to be 2 times the area to the right of 3.379. And since we know that the area to the right of 3.379 is between 0.001 and 0.005, then the p-value will fall in between 2 times that interval, which means it will fall in between 0.002 and 0.01. Okay, so we're given that the p-value is somewhere between 0.002 and 0.01. So now we will compare this to the significance level. So we're testing at a 5% significance level. So alpha is going to be 0.05. And now since the p-value is smaller than alpha, okay, so the p-value is bigger than 0.002 but smaller than 0.01, the p-value is going to be smaller than 0.05. So because the p-value is smaller than alpha, we will reject the null hypothesis. This means that there is sufficient evidence to conclude that the mean weights, or that there is a difference, between the mean weights of chickens.